Welcome to March 24th, and we are talking about the acidity of the alpha carbon of carbonyls. Yesterday, I introduced you to the new chapter. We're on chapter 22 of your Wade book. And in your POGL exercises for this chapter, we're going to do 23A, 23B, and 23C. I will be doing these online videos to go over your POGL exercises. You will turn in your additional questions of your POGLs by email. And then if I give you just some kind of online video kind of following the book and the reactions, I might give you a reaction or something, so you can attach that onto your additional questions for your POGL. Each one of the POGLs, 23A and 23B and 23C, will be basically, that's going to be 15 total POGL points. And this is going to make up your CJM score. Okay? With output and with output. Alright, so let's start with on page 262 in your POGL book. So you have the model, and I want you to work on this. And then we have base. This is model 1. And it says review effects that stabilize a conjugate base. And there's 5 of them. So size, that's the size that the negative charge resides on. So you remember HI versus HF. You do your conjugate bases, right? And this one's bigger, so more polarizable. So because the size, this is a more stable conjugate base, and therefore HI is more acidic than HF. Okay, number 2, the formal charge. 3, electronegativity. So you want your negative charge on your more electronegative atom. 4 is resonance. So this is why a phenol is more acidic than just a regular alcohol, because you have resonance stabilization. And what is resonance worth here? About 10,000 times more acidic. And then we have 5, induction. And you just finished up induction when you were looking at this acetic acid versus this acetic acid. And the electron withdrawing group of fluorine does an inductive effect on the carboxylic acid. Okay, so that is your model 1. Questions, Q1. Consider the carbonyl compound. What is this? So, what Greek character is given to the carbon, this carbon, directly attached to the carbonyl carbon? Alpha, right? How many alpha carbons are there in this aldehyde? So if this is R equals H, there would be 1 alpha carbon. Now if this is a ketone, the question is how many alpha carbons? So this would be an alpha carbon and this would be an alpha carbon. So that would be 2. That was a ketone. Label all remaining carbon atoms beta, gamma, delta. So this is beta, and this is gamma. If we had another one, it'd be delta. Any hydrogen attached to the alpha carbon are called alpha hydrogens. So we have 2 here. 1, 2. Draw in the alpha hydrogens for the carbonyl shown. So draw these alpha hydrogens in. Those are going to be acidic. Consider the reaction of an aldehyde with a base shown on model 1. How many different kinds of hydrogens are there in the aldehyde? Well, you have alpha hydrogen, you have beta hydrogen, you have gamma hydrogens. And then you have the carbonyl hydrogen. That was an aldehyde. Draw the conjugate base, the results from the removal of the indicated hydrogens below. Okay, so we're on 2B. And I would like for you to try to do these, and then you go back and look at this lecture video. So if you have a base, this says remove hydrogen attached to carbonyl. Now, so this hydrogen, it's not acidic, okay? So they're trying to show you the point here. So if the base removes this, then the conjugate base is this right here. Okay? And there are no resonance structures. If we take this same compound, this aldehyde, and we remove the alpha hydrogens, so the alpha hydrogen, well, then we can draw resonance structures. Okay, and if we remove the beta hydrogen, this is your alpha, here's your beta. Let's draw the hydrogen in. No resonance structures. Okay, so that completes page 1, page 262. 2B, draw all possible resonance structures of these conjugate bases. That's what we did here. Which conjugate base from 2B would have the lowest energy? So obviously, it's the one with the alpha hydrogen because of the resonance structures. There's 2. Circle the hydrogen on the aldehyde that takes the least energy to remove. Okay, so this is the least energy to remove, the most acidic hydrogen. So that's going to be your most acidic hydrogen. And it's going to be your alpha hydrogen. All right, so now we're on to question 3. 3A. A base can also act as a nucleophile. A Lewis acid, so a Lewis acid, and where you saw Lewis acid is like aluminum trichloride, and you remember the chloride here, and it basically accepted a pair of electrons here to make this a strong electrophile. Okay, so this is your Lewis acid. You did this in ease. Electrophilic aromatic substitution, accepts a lone pair. Okay, so a Lewis base, A Lewis base then would donate electrons, and a Lewis acid accepts electrons. So if you look at another Lewis acid is like BF3, okay? So if you draw out the boron Lewis structure, what's the hybridization of boron? sp2. So that means it has trigonal planar, and it basically is flat. So this is flat. Everything's 120 degrees. And then above the boron you have, and below you have an empty p orbital. And so a Lewis acid will accept lone pairs into this unhybridized p orbital. Describe what is the same between a Lewis base and a nucleophile and what is different. So same between a Lewis base. So a Lewis base will donate the electrons, and a nucleophile will donate its electrons. And so when we think about bases, though, we think of it donating its electrons to hydrogen, okay? But when we think of a nucleophile, it's donating its electrons to carbon. And this is going to be important because when you remove, why is this important? When you remove that alpha hydrogen, that acidic proton, you create a carbon nucleophile. Okay, you're creating a carbon nucleophile. And that's what you're going to see here in 3C. Well, maybe you're not. So here you have a nucleophile, and the carbonyl will react. You got a delta positive and delta minus. This carbonyl will react at that electrophile and make your tetrahedral intermediate, right? These two electrons become here. Those electrons go up here. Okay, so you have a tetrahedral intermediate. Now, 3D. The reaction shown in 3C competes with the acid-base reaction. And in your groups, discuss how the base, the nucleophile, could be altered in order to force the acid-base reaction to proceed preferential. So they're saying, how do you get the base, which is also a lone pair, to take the alpha hydrogen and generate your enolate, which is the same thing as if you redrew this, right, and you put in your monkey face here. Okay, so that's the same thing. That's just your resonance structure. So the question is, how do you make 3D work, or this reaction work, over 3C? And so the answer is to have a sterically hindered base. Use a Hoffman base. And there is a particular Hoffman base for this chapter. So if you remember in my discussion yesterday, I talked about the different bases you're going to be looking at for these chapters. And what they're talking about here in your POGL is under 4. So question number 4, page 264. Determine which of the compounds would act predominantly as a base, a nucleophile, or both. So you have this one, and this one's sterically hindered, LDA. You need to know that structure, and this would be predominantly a base. Okay, it's too hindered to act as a nucleophile. That nitrogen cannot get in with its lone pairs to attack a carbonyl. Okay, this one, okay, you've seen this, lithium NH2. You've also seen this as sodium amide. Okay, it's the same thing, sodium amide. You use this to deprotonate an alkyne. That's where you first saw this base, okay? This would act as both. It's still small enough that it could also go after the carbonyl here and act as a nucleophile. So this one's both. This base, or this one would be a base, okay? Dimethylpyridine, okay? And then this one here is a Hoffman base, okay? So that's tert-butyl, well, it's actually sodium tert-butyl alkoxide. You've also seen it with potassium. And those are your Hoffman bases. They're sterically hindered. Draw the most likely product that forms when the reaction of butanal reacts with LDA. So 4,4B. There's your butanal. And this is your lithium diisopropyl alcohol, or diisopropyl LDA. Diisopropyl amide. Lithium diisopropyl amide. All right, so now you got to look for your alpha hydrogen, and it's going to take that alpha hydrogen. All right, so this is your conjugate acid, and then you're going to get well, let's do this one. The lithium would hang out there. So this is your enolate, okay, which would be the resonance structure with this. Hopefully you're getting this in your notes. Here's your enolate, and that would be your conjugate base. So here, this is your acid, and this is your base. Now your acid, I'm going to go ahead and tell you your pKa. Remember that was a 20. That's an aldehyde. Now you're looking at your alpha carbon. I told you yesterday to start memorizing that. Here you have a pKa with about 36. So it definitely goes towards the product. 36 minus 20 is 16 zeros. Okay. We are going to do Model 2. And then tomorrow we'll do Model 3. Okay, so I'll break this up just like I would in class. Let's do 2 models a day. Okay, that's what we're going to do, 2 models a day. And then you all do your problems in your sapling. So Model 2, enols and enolates, ions. At this time you can try to work your problems and your questions as I draw out Model 2. This is an enolate ion. Okay, enols and enolate ions. And I told you yesterday that that is something we need to know the difference. So we'll work through these questions. What is the main difference between enolate ion and the enol? The biggest difference I see is the this negative charge, okay? So it's the negative charge. Here you have a hydrogen on the oxygen, okay? So there's the difference. Enol is like ene, double bond, carbon, double bond, ene, and OL is an alcohol, okay? So there's your ene-all. Here you have the ene, carbon, double bond, carbon, and then it's an olate. So there's your negative charge, the 8 ion, okay, enolate. Which hydrogen is removed from the enolate ion and the enol? Okay, so it is this alpha hydrogen that is removed. The base comes here, removes that hydrogen to generate this carbon anion. Or to go to the enol, this oxygen basically takes the hydrogen and then those electrons go there to make the enol. So it's the alpha hydrogen. Is base used to form the enolate? Yes. Is base used to form the enol? And the answer is no. So there's no base here. So a lot of ketones and aldehydes, they will be in their enol forms. And this word is called tautomerization. The interconversion between a ketone and enol is an equilibrium reaction. So you can see here, equilibrium reaction. What is the keto-enol interconversion called? You want to write that word tautomerization. Which form is favored? Obviously, here the keto form is favored. Why? You have a larger arrow. The carbonyl is more thermodynamically stable, okay? So the carbonyl is more thermodynamically stable. So whenever you're talking about an equilibrium reaction, you're talking about thermodynamics as opposed to kinetics. Okay, so then we're going to work problems 6, 7, and 8, and then we'll call that day. Okay, so 6. Draw the enol form of the following ketone. Okay, so you can draw in your hydrogen here on the alpha, and the enol form would be this would be your enol, and then you could draw equilibrium arrows. Draw the so that's A. B, keto form of the following enol. So this is your enol, and they want the keto. So that goes there. And this has one hydrogen, there's one hydrogen, and basically these both go back to here, and this is your keto. And that would be your equilibrium arrow. Okay, for 7A, unsymmetrical ketones can form two enol forms. Okay, so we have an unsymmetrical ketone. We have this compound here. We'll go ahead and draw in our hydrogens, our alpha hydrogens. So that's an alpha hydrogen, and that's an alpha hydrogen. Draw the two enol forms expected from the following ketone. So we could get this one, or we could get this one. Okay, now remember this is a thermodynamically stable, so both the keto is going to be more thermodynamically stable, but I'm going to give this one a bigger second arrow. And this would be more stable than the other because you're looking at a 1, 2, 3, a tetrasubstituted double bond, carbon-carbon double bond, whereas this is a tri-substituted. So this one would be more stable. It says circle, so for 7b, circle the enol that would be the most stable. Think about the double bond stability. This is called the thermodynamic enol. All right, so our next one is 8. Consider the ketoaldehyde shown below. So this is a keto, and this is your aldehyde, okay? So this is your alpha, and this would be alpha. But I just want to show you something too. When you have an aldehyde here, and this is alpha, this carbonyl is a beta. And this actually is a new functional group that you're going to need to know in this book, in this chapter. It's called a beta keto carbonyl. And the reason why that's going to be important, you're going to see that that's your product of the Claisian condensation. And Claisian is your 23C, okay? We'll be doing aldol reactions. And aldol products that we kind of talked about last week or yesterday is your products are this. So there you have an alpha, beta. So this is a beta hydroxy aldehyde, or you could say carbonyl. And then if you heat this, then you lose water. So you're going to lose that other alpha hydrogen here. And you're going to lose this oxygen and that hydrogen. That's going to make up your water to give you an alpha beta unsaturated aldehyde. It's going to be very important to recognize which are your products for the Claisian and the aldol. Okay, so let's go back to this problem here because we're going to finish this up. And it says, label all alpha carbons. So there's an alpha carbon, and that's considered an alpha. Let's draw in our hydrogens. Okay, so there's 2 alpha carbons. Draw the 2 possible enolates that could be formed by removing each alpha hydrogen on a reaction with base. And then draw all resonance forms. So if we have a base here that removes this first one, all you do is redraw this, okay? And then draw in your monkey face here, okay? And then, of course, you can draw your resonance structures where these go here and these go here. Resonance arrows. There you go. Now, what if our base took the other hydrogen? Okay, so what if the base took this one? So you redraw. Okay, now we draw our resonance structures. And then we also have another one here where it could have gone the other way. All right, so this has 3 resonance structures. This has 2 resonance structures. Based on the stability of the conjugate base, the enolate, discuss which hydrogen is the most acidic in the above. Ketoaldehyde is a keto, beta ketoaldehyde. Beta ketoaldehyde. It's going to be this one, right? The one in between the 2 carbonyls. And that's because you can draw more resonance structures. I think if you look that up in yesterday's chart, you can check me out on this, but I think this pKa is a 9. I think so. You can look that up and check that. Okay. Go ahead and work. We'll talk about Monday's question. I know you still have that question out. I'll come back and do Model 3. You should be able to do problem number 11. The additional problems on page 268. So problem number 11, page 268 are your additional problems. And then we'll finish up with Model 3. You will need to get a reaction sheet for Model 3 because it's one of the reactions you need to know for this chapter. And I will, at some point, summarize all of the reactions you need to know in this chapter in one lecture. Okay, talk to you later.